Here we have a video on our special factor pattern, the sum and difference pattern. Remember, the sum and difference pattern, when you distribute this out, becomes a difference of two perfect squares, a squared minus b squared. You can FOIL this out really quickly to check. A times a is a squared, that's the outsides. That's the firsts. The outsides would be a negative AB, and the insides would be a positive AB. Whenever you have the same terms with one sign opposite on one of the terms, this will always happen. You'll always get opposite terms that end up being added together. That always cancels each other out to 0. Then I've got positive b times negative b, which is always going to be negative b squared. So the sum and difference pattern multiplies to what we call the difference of two perfect squares. The difference of two perfect squares is probably one of the easiest factor patterns to recognize because it literally is a binomial, two terms. There's a difference between them, and they're both perfect squares. You can pause now and find the product of all of these binomial pairs so that you can see where the middle term cancels out. In the first example, I get the first to be 4r squared, the outsides negative 2rs, the insides positive 2rs, and the last negative s squared. The positive 2rs and the negative 2rs add to 0, and so I'm left with a binomial of two perfect squares and the difference between them. Looking at the example in blue, I've got 4x squared minus 3 times 4x squared plus 3. Same terms inside those binomials, but signs on one of the terms are opposite of each other. Even though I've got an x squared in that binomial, I can still multiply those together, and I can clearly see that 16x to the fourth is indeed a perfect square. Remember, a variable with a variable with an even exponent is a perfect square. So x to the fourth is a perfect square, x to the sixth, x to the eighth, x to the 10th, x to the 12th, etc. If it's an odd exponent, then it is not a perfect square. And so I have 16x to the fourth minus 9 for that one. Looking at that black example, it looks like I don't have the same pattern here, but I do. I just need to commute that first group from negative 2y plus 3x to 3x minus 2y, and then I can clearly see that I've got a difference of two perfect squares pattern here as well, or sum and difference pattern. And so all of these are difference of two perfect squares, and that's what factoring. So here, if you're presented with the difference of two perfect squares, can you get back to the sum and difference pattern that created it? It's really easy. You just check for binomials, make sure that all of the terms, both terms in the binomial are perfect squares, and then you've got the difference between one of them. Sometimes you'll have to factor out a red flag or a -1. And there really isn't any order to descend in, so usually that's it. But after you do GCFs and red flags, like we always do, you have difference of two perfect square patterns. So go ahead and pause and see if you can do these on your own. All right, let's run through these really quickly. 4r squared is a perfect square, and s squared is a perfect square. And so factoring this would be 2r minus s times 2r plus s, because I take the square root of those and put them in their binomial patterns. One would be plus and one would be minus. 16x to the fourth is a perfect square, and -9 is a perfect square. So that would be 4x minus 3 times 4x plus 3. 4x squared minus 3 times 4x squared plus 3, because the square root of 16x to the fourth is 4x squared. Those are the two things that I had to multiply together to get 16x to the fourth. 9x squared minus 4y squared. The square root of 9x squared is 3x. The square root of 4y squared is 2y. And so I put those two things in brackets. One's positive and one's negative. It actually doesn't matter which one is negative and which one's positive as long as they're you do one of each. Remember, we always have to factor out GCFs and red flags first because that could potentially reveal a pattern to me that's not necessarily there. If I look at 8x squared minus 32, That is not a difference of two perfect squares. But when I factor out the GCF of 8, I'm left with x squared minus 4, which is a difference of two perfect squares. So I'm not done until I double check everything and make sure that I haven't revealed a pattern by factoring out a GCF. X squared minus 4 factors to x plus 2, x minus 2. Looking at this one over here, I have a GCF of 2, a GCF of s, and I'm left with, when I pull out that 2 in the s, p squared q squared minus 9r squared. It seems a little bit complex, but p squared, q squared both have even exponents, so they are perfect squares. When I take the square root of p squared, q squared, that's just p times q, or pq, because pq times pq is p squared, q squared. The square root of 9r squared is 3r. I repeat that grouping with one being negative, one being positive, and don't forget your GCF out front. And that is how that one factors. Let's look at this last one, x to the 4th minus 16. I love these. They're kind of cool. So x to the 4th is a perfect square because its exponent is even, and 1 is a perfect square. That's the leading coefficient there. And 16 is a perfect square, so I know it fits the difference of two perfect square patterns. The square root of x to the 4th is x squared. The square root of 16 is 4. I repeat those terms in parentheses. One's going to be positive and one's going to be negative. But take a look inside those parentheses and see what happened. X squared plus 4 and x squared minus 4, those are both perfect squares again. Now looking at that first group, x squared plus 4, it's not the difference of two perfect squares, so I can't do anything else there. But x squared minus 4 is the difference of two perfect squares. This is factorable, so I take the square root of x squared, which is just x, the square root of 4, which is 2. I repeat that pattern. One's positive, one's negative, but I can't forget the piece that was already out there to start. So this x plus 2 times x minus 2 came from this binomial up here of x squared minus 4. And so the final answer is x squared plus 4 times x plus 2 times x minus 2.